mixed with no regards for the differences. There is a technical difference, and when you start, say, covering Java next semester, then that's certainly an object-oriented programming language. But C is not an object-oriented programming language, but it does have basic objects, which are called structures. Basically, for either structures or objects, the whole point of defining those things is something called encapsulation. And the motivation for this is that a lot of the built-in types in C, like integers, doubles, chars, they're really limiting, right? It means that everything is basically a number. Everything is either a whole number or a fractional number or a number corresponding to a character in the ASCII text table. Not everything in real life, though, is a number, right? Real-world entities are made up of multiple pieces of data. For example, yesterday you did your lab on file I/O, and one of the things that you had to do was you had to load up a file of state population data, where you had a state name and a population, right? There are two pieces of data that logically belong together. Or you had to, I think that the other exercise was that you had to load up data on MLB teams from a while ago. You had a team name, you had maybe a city, you had a payroll, you had a whole bunch of different pieces of data that made up the whole, right? So real-world entities, they are made up of multiple pieces of data. And again, one of the examples was from Lab 10, where you have a team data, right? And when you worked with these things, you kept a lot of different pieces of data in different arrays. Hopefully, you did take the opportunity to look a little closer at the code that handled all that stuff. In particular, there was a sorting function. That sorting function actually took multiple pieces of arrays, like wins, losses, team name, and a bunch of other stuff, and it had to sort them all. Well, all these pieces of information were split across different arrays. So when it switched these two things over here in this array because it was out of order, it also had to switch these two things in this array and switch these two things in this array. And you can see that kind of manual bookkeeping is very, very limiting, right? Every swap that when you sorted it, every swap basically had to swap every value in every single array. It's really easy. It was really easy to screw this up, right? Bookkeeping is hard. Right? So what we want to do is we want to alleviate the need to do this bookkeeping, right? And eliminate this inconvenience. It was really convenient to store related pieces of data in different arrays. Right? So that's where encapsulation comes in. Encapsulation. Right? You might be familiar with this plain old English word already, but in the context of computing, in the context of programming languages, it actually consists of three different things. It consists of the grouping of data, right? So in other words, taking all those pieces of data, the team name, the wins, the losses, maybe the payroll, something else, right? The city that they're in, taking all those 5 different pieces of data and encapsulating them in one logical unit called, say, maybe a team, right? That's the first part, grouping of data. 2 is the protection of data, right? And 3 is the grouping of functionality that acts on that data. Right? So C, being a non-object-oriented programming language, only supports number 1, the grouping of data, through what are called structures, and that's what we're going to be dealing with today. Number 2, the protection of data. That's really more of a pure object-oriented programming thing, where not only do you group the data together, but you protect it from the outside world, and you control access to the data and side effects of changing the data. The grouping of functionality that acts on that data means also that you're taking all the functions that act on that data, that sort that data, that print that data, that do whatever else, and you're taking that functionality and grouping it in within the same logical unit. That would be classes in Java, where you've got both state and behavior, where you've got variables and functions or methods that act on those variables. You don't have that in an easy manner in C. So we're going to only focus on number one, the grouping of data. So encapsulation, encapsulation in C, basically C again only supports number one, right? The grouping of data. This is sometimes referred to as weak encapsulation because it doesn't have those other two, right? C provides this weak encapsulation through structures, right? Or simply just for short, we call them structs, right? And let's just get into the syntax right away here. So I'm going to go ahead and go through an exercise here with you to define a student structure. So what pieces of data should be associated with a student? To get started, let's at least get one or two things. An NUID, right? A unique identifier. What else? Yeah, your name. So your name, like let's take mine, Christopher Michael Burke. Right? Should all of that be grouped together, you think? What if somebody decided to refer to me as Burke, comma Christopher, or Burke, comma Chris, or C, period, space, Burke, right? So do you want to split that up anymore? First and middle and last. So already we're decomposing one larger object into multiple smaller objects. So to do that, let me go ahead and get you started. Type def struct. Where have we seen that before? Where have we seen type def? Enumerated types. You define the type of enumeration and then you called it something. Now we're doing something different. We're defining a type of structure instead. And again, it is going to be an abbreviation because if you can save bytes 40 years ago, you did. And we'll call it a student, right? Just like we did with, let me scroll, there we go. Just like we did with the enumerated type, we provided the name at the end with a semicolon. Now already I heard that there are going to be, I'll just keep it first name, last name, forget about the middle name for now. What types are those? Well, they sound like strings to me. First name and maybe a char star last name. Already we're seeing a difference with the syntax with an enumerated type. With an enumerated type, an enumeration was a list. A list was delimited by commas. This is not really a list anymore, right? The order doesn't really matter. And so what do we have delimiting these? Semicolons, okay? I've got the first name and the last name. I also heard at the beginning an NUID. What is an NUID? It's a number, right? So, my NUID is 35140602, right? So it's every NUID is 8 digits long, right? That's certainly small enough to fit into an integer, but how many people have an NUID that begins with a 0? There's got to be at least, well, 10% of you, right? They're randomly assigned. How many people have a 00? No? Oh, one over there. I've never seen a 000. Anybody have a 000? Okay. Well, at least 1% of you has a 00 beginning with that. So, do we want to model this problem with an integer, int NUID, or do we want to model it with a string, char star NUID? Right? There's no right answer here. One answer, if you want to go with a string, that means that you're going to handle those leading zeros manually. It just has different implications for how you handle the data. You're going to have to use strcmp to compare a string instead of using equals equals to compare a number. It has the advantage here, if we do it with a string, that when we print it out, we don't have to pad it out with zeros. On the other hand, if we use an integer, well, then it gets it gets a little bit more complicated in other areas, but less complicated in others, right? Now we can use equals equals for equality testing to find a student with a particular NUID. But at the same time, if we print it out, we're not going to have that leading zero for the 10% or the 1% of people that have leading zeros in front of their NUID. This is a practical problem. I have heard of stories where somebody's NUID did not work because of leading zeros. Have any of you experienced that yet? No? Okay, hopefully they've gotten the bugs in various systems worked out. The library used to be notorious for that, that it wouldn't work or it wasn't printed correctly or something like that. I still have issues if I'm cutting and pasting a bunch of NUIDs into Excel. Excel wants to convert them all to numbers, and it gets rid of all those leading zeros, and now the formatting is all off. So votes. Do you want to be integer or char star? Char star? Okay. Right. All the data is looking uniform, though, right? I do want some variety here. Give me a double, right? Give me something to model a student that might be a double. GPA, okay, good. What else might you want to put there? A year of, what's the most common, year that you started, maybe, year that your graduation target date. What's something that everybody has, though? Social Security number. You're not allowed to do that anymore. That's why we have NUIDs in the first place. How about a date of birth, right? So, I don't know, date of birth. Right? How do we model a date of birth? This goes to the heart of encapsulation, right? I want this entity, I want this thing to work with, and I don't want to have to worry too much about the details of it, right? Of how it represents its date, right? There are lots of different ways of representing a date. What's one suggestion way back there? Okay, so 3 numbers, right? The year, the day of the month, and then the month, right? We could do that. In fact, let's go with that solution. But what are some alternatives? Yeah. So it could just be with hyphen separators, or with backslash separators, or whatever they are, / separators. In other words, just a single string, right? Another way of representing a number is a single number. And this is how Unix does it. If you've ever heard of the Unix Epoch, let me go ahead and pull up a browser here. A Unix Epoch. Right. On a Unix system, the time and the date is a single, very large number. Right. It is a number representing the number of milliseconds that have passed since the Unix Epoch, which is going to be January 1st, which was a Thursday apparently, 1970. So we've got this big number that's being counted, and it's always going up. In fact, do we have an epoch converter? Let's see if we've got a live. Come on, if we've got a live counter here. There we go. All right, it's not going up any. There, now it's going up every so often here. But there's the current Unix epoch there. It's counting up the number of milliseconds since January 1st, 1970. And then you can take that one number and then you can convert it to months, days, years, whatever you want, just through mathematics. Now there is a problem. There is a Unix Epoch problem. Right? That there's a Unix Epoch apocalypse. At the end of the Unix time will occur on January 19th, 2038. So in about 20 years now, there will be an overflow. Because numbers that use, I believe, a 32-bit number to represent this number, the number of milliseconds since 1970, will no longer be able to represent the number of milliseconds since 1970. So it will turn around and it'll be something like 68 years before 1970. So it'll be 1902. We've heard this problem before, haven't we? We're in the popular culture 18 years ago, hint. What was it? The Y2K, right? That they used 2 digits to represent the year. Here we're using a 32-bit number to represent a number of milliseconds since an epoch. There's always going to be this issue somehow. And I've seen plenty of designs. In fact, how do we represent semesters here at UNL? Right now, the semester code is 1. All semester codes begin with a 1. And then it's 2018, so then it's 1-8. And then this semester began in August, so then it would be 8. So this semester, fall 2018, is 1188. Spring semester will be 1191. Right? So using one number to represent a month, that's fishy, right? Because you can never have anything beginning in November or December. And then using 2 numbers to represent a year, we did not learn our lesson, did we? And then the leading one is just so that everything is sortable. And so we continue to make this mistake over and over again, thinking that, oh, well, in 70 years, we won't have to worry about this, right? People will have always all upgraded to 64-bit systems. Most systems are upgraded to 64-bit systems. There are plenty of systems out there that I'm sure are not. So we continue to repeat the same problems over and over and over again. Let's not repeat that problem, right? Let's design our date of birth to be, as you said back there, 3 numbers. So I could do something like, I don't know, int date of birth day, int date of birth month, int date of birth year, right? And then go back and fix the syntax there. That even seems icky, right? I've got 3 pieces of data that belong together. What should I be doing to them? I should be encapsulating them in another structure. So let's go ahead and create another structure here. Type def struct. I'll call it date. Date, there we go. And instead of doing this, I'll go ahead and bring these 3 down here. And I'll just call it day, month, and year. Year, there we go. There. Now I've got that. So if I want to define a structure like this, great, I can call it date. There's already a built-in structure called tm underscore, which is time underscore, I think t, built into the standard libraries. We're not going to use it though. It's kind of difficult to use. Don't worry about it. Instead, let's go ahead and use our own here. So date, date of birth, or birthday if you want to call it birthday instead, right? There's still something that seems wrong here. Think like a dumb compiler. Go to that first line, type def struct. Okay, you're creating a structure here. It consists of an NUID. I know what that is. I know what a char star is. First name, last name. I know what those are. They're char stars too. Double GPA. I know what that is because it's built into the language. Date. That's not built into the language. That must be a user-defined type. But have you seen, as a compiler, have you seen the date yet? The definition of a date? No. Where's the definition of the date? It's down below. Does that sound right? Can you use a variable up here while you've declared it down here? Nope. If you're going to use x up here, it needs to be declared before that. Likewise, structures. The order that you declare structures in is important. I'm going to move that up to the top. Now I've got a clear definition. Okay, I know what a date is. It's just these 3 numbers. Oh, down here, a student. I know what a student is now because I know that that date is up there. This has a name. When a structure or object owns another structure or object, it is called composition. Right? Well, why is it called composition? Because one structure is composed of another. Right? A date is composed of 3 numbers. A student is composed of 3 strings, 1 double, and another structure. Right? So you have this kind of parent-child relationship here with respect to composition. Object-oriented programming, there's a different notion of parent-child, and I'm not referring to that. I'm referring to one object owns an instance of another object. So in other words, you've got, say that the student is the parent, it owns the date as a child, right? So the child has to be defined before the parent. That's kind of backwards, but that's the basic idea, okay? What other things do you see with respect to the example that I just did? You have various naming conventions, right? We're going to go ahead and use upper camel casing for structure names. Note that both date and student were capitalized on the first. If it was multiple words, then each additional word would be capitalized with the first letter, lowercase on everything else. Use lower camel casing for members, right? Member variables. You use no, I guess this is not a naming convention, but syntax issue, is you use typedef struct to declare a structure, curly brackets to define the member variables, each of which is separated by a semicolon. Good. Also, more generally, structures are usually declared in a header file. Say for our example here, we're defining a student. We would generally call that student.h, right? I would put both of these declarations in there, or if I really wanted to separate things out, I would put date into date.h, and then I would include that header file in this header file over here. Although if you get really complicated there, then you need to bring in something called an include guard, which is not something I want to get into in this course. Basically, it's another preprocessor directive that says if this header file has already been included, don't include it twice, because then that would be two definitions of the same thing, and that's what's called an include guard. Again, we're not going to get into that. Again, structures may contain other structures as members, but the order in which you declare them matters, right? Child structures must be declared first, right, before the structures that contain them, right? All right, so that's the basic declaration. Once you've declared it, you can use them, just like any other variable, using structures. Right? So once declared, you can create variables of that particular type. Right? I'm just going to go into code mode here and demonstrate it. There we go. So I'm going to create a student. I'll make myself into a student here. Student me. I'll just go ahead and declare myself here. Right? Now, how am I going to set my first name? How am I going to set my NUID, et cetera, et cetera, et cetera? Right? Well, once you've declared it, you use what's called here's the technical term. It's the direct component selection operator, but we like to call it the dot operator. Oops, what did we say NUID was? You know what? I'm going to go ahead and veto that, and let's go ahead and make it an integer, just so that we have an integer that we can actually use here. Right? So I'm going to go ahead and set my NUID to 3110560. There we go. All right. There. That's my actual NUID. There's no security issue there whatsoever. Who cares? It's not like your NUIDs are tied to your account. Mine is not. And that's called the dot operator. Why do you think it's called the dot operator? Me dot NUID, because it's a dot, right? That's why we call it the dot operator. Well, what if I wanted to set my name? Me dot first name is equal to Chris. Is that going to work? Can I just create? Can I just reset a string? No. What do you need to do to a string? If you want to copy chris into this string over here has to exist first. What is first name right now? First name is just a pointer. What's it pointing to? Nothing. Right? We need to make it point to something first. So let's go ahead and make create enough room to hold my first name. How do I do that? Well, I need to call malloc. Me.firstname is equal to a call to char star malloc size of char times, and how many characters am I going to need here? I'll just go chris, just 5. Is that enough? I need one more. Why? For that null terminating character at the end. So times 6. Now, once I've got enough room, it's actually pointing to this string of length 6, and I can put chris into it. I still can't just simply set it equal like this, right? That might even get past the compiler. Hopefully there would be some really serious warnings there. But it would let you do that because that's a string. You're just making it point to a different string, right? But the right way of doing this is what? strcpy. Into my first name, or me.firstname, the value chris. Right? Okay. Well, following that, let's go ahead and do the same thing for last name. Oops. Last name. Cut, paste, Burke, and B-O-U-R-K-E. 6, so it's actually 7. Great. All right, so I've got my NUID, my first name, last name. I need to set my GPA here, so me.GPA, let's say it's 3.5. Right? Don't shoot too high, right? All right, me.date of birth, right, is equal to, whoa, we've got an issue here now. Date of birth. That's not just one number. I can't just set that to whatever, right? How am I going to have to set my date of birth here? Date of birth is a structure. How do we access the day in that structure? How did I access the NUID in this structure? The dot operator. So all you need to do is keep applying the dot operator. Me.date of birth dot day is equal to the 9th. Me.date of birth dot month is equal to July. So it is July 9th. Me.date of birth dot year is equal to 1990. Right, there we go. Yeah, I'm in my 20s. All right, good, you're not laughing. All right, that's a good sign. All right, so there's my date of birth, right? That seems like a lot. What was I doing, especially on the first name and last name? I was copy pasta, right? Don't copy pasta, it leads to spaghetti code. This seems like, well, a dozen lines of code here just to create one person. Presumably, you're going to want to be reading an entire roster of a class of students or something. Are you going to be cutting and pasting these same 12 lines of code over and over and over again? Maybe you could put it all into a loop, and then for each person that you're reading from the file, you have those same 12 lines of code. But even that seems kind of redundant. What should I be doing here? What's a better solution than repeating myself? Yeah. Yes. Write a function, right? So, solution. Write a function, right? Now, in object-oriented programming languages, these are usually called constructors because you construct an object. C is not an object-oriented programming language, so we have a different term for it. We call them factory functions. You can create a factory function that automates, not automates, but yeah, basically automates, that more conveniently allows you to construct new instances of a structure. Right? So what would that look like here? Let me go ahead and go back into C mode here. And let me see, do I have a... All right. What should we call this function first of all? We could call it student factory or something, right? That seems kind of impersonal though. What are we doing? We're creating a student, right? So create, right? Student. Probably just want create student because, well, what are you creating, right? Put the name on the function of what you're doing. So we'll go ahead and create a student here. Sorry, it should stick down here. There we go. What should its return type be? What I'm going to do is I'm going to take all that data, my first name, my last name, et cetera, and I'm going to give it to this factory function. It's going to take all that stuff, create a brand new student instance, and give it back to me. So its return type needs to be a student. that's not going to be very a good design. And we're going to come back and revisit this in a second. But first of all, let's go ahead and at least start designing this function before we fix it. Right? It's going to take all the things that you need to that go into a student: an NUID, char star first name, char star last name. Right? And here's a style tip. These things can get quite long, so it is perfectly fine to go ahead and break them, line break them on each one of these parameters here. First name, last name. What else did we have? Double GPA, right? And an integer for your day, int month, and int year. There we go. For your date of birth. And you can call those other things and be more descriptive if you really want to. Okay? Well, what's it going to take? All I'm going to do is I'm going to take this code up here, cut, paste. Oops, I didn't want that. It's going all the way over here. So let's go ahead and fix this. We've got to fix it anyway. Me.NUID should be that NUID. Right? And what is me? I need to create another student. It's not me anymore, so I'm going to go ahead and call it S instead. Right? And I'm going to do everything else that we just did. So S dot first name is equal to Malik, and it's no longer going to be hard-coded to 6. What should it be? S dot first name, and it's not going to be Chris all the time. It's going to be first name, right? So how big of a string do you need to accommodate first name in this example here? String length. I need to call string length on this. So times strlen of first name. Right? Is that enough? Plus 1. Always for that null terminating character. And it's not necessary, but you can go ahead and put those into parentheses there. Right? And then we can copy it over. S.last name, similar, is going to be a call to char star Malik, blah, blah, blah. There we go. And last name, there we go. And then I will copy over into s.last name, not my name, but last name. There we go. And no longer me.gpa, but there we go. S dot, and S dot. There we go. And it's not, it's going to be day, month, and year. There we go. Okay. Oh, and it's not 3.5 anymore. It's going to be GPA. There. Now I've got a factory function, and I can churn these things out as much as I want. Right? If later on in the code, let me go ahead and go later on in the code here. You can go ahead and create a student, Joe, let's say, and equals create student. And what you have to remember the order of things though. So his NUID is 1, 2, 3, Joe, Schmo, GPA of 4.0, say, and he was born on 1/1/1970. So he was born on the Unix Epoch there, right? Or you can have student Jane equals create student 5, 6, 7, 8, right? And then Jane Doe, also 4.0, born 1 day later, 1970. There we go. So now you've encapsulated you've taken all that functionality of creating this object, creating this structure, put it into a factory function, and now you can reuse that factory function all over the place. Right? There is a problem here though, and to illustrate this problem, let me go ahead and grab my definition up here, and we're going to go into REPL, if I've got it up. Yeah, here we go. I'm going to put my definition up here, and I'm going to ask, I'm going to write some code here to see how big this structure actually is, %d. Now, how do I tell how big an integer is again? Size of. How do I tell how big a double is? Size of double. How do I tell how big a student is? That is, how many bytes a student requires. What do you think? Size of. Once you've defined it, it's just another type in your code. So size of student. Right? Now let's see how big a student is. First of all, can we guess? So we've got basically 3 integers for the date, another one for the NUID, 4 bytes each. That's going to be 16, right? I'm guessing that a pointer is going to be 8 bytes. So that's another 16 on those 2 pointers right there. So that's 32. Double is going to be 8 bytes, so that's going to be 40. So I think my guesstimate here is that it's going to be 40 bytes. Let's find out. Oops, what did I do wrong? Oh, thank you. I can't believe I did that. I'll fix that in the notes later on. There we go. Oh, 48. All right. So there's an extra 8 bytes in there somewhere. Probably there is something called, I forget what it's called, but it's called framing, where a compiler will actually take a structure, and then it may only require 40 bytes, but it's not efficient to do 40 bytes. It's more efficient to do, say, 50 bytes or something like that. And so it will waste, it'll burn this last 10 bytes over here and always allocate a multiple of 4 or a multiple of 8, depending on the system. So it's at least 48 bytes here. Let's go back to my factory function here and think about what's happening when that student me should not be there anymore, sorry. All right. Let's think about what's happening here. I give it a whole bunch of data. It creates this student, and then it returns it. There are 2 problems here. The first problem, well, there's really only one problem here. The problem is it's returning 48 bytes. Now, that's not that big of a deal. If you return an integer, you're going to be returning 4 bytes. If you return a double, you're going to be returning 8 bytes. 48 bytes is quite a bit, though, is getting up there. But now think of a structure that represents, say, an MP3 file, or a structure that represents an image file, or a structure that represents some large binary file. It's got a bunch of binary data in it. Say that it's 10 megabytes of data. Are you going to be able to return 10 megabytes of data? How is data returned from a function? Remember, that's stack, right? It's going to be allocated on the stack, and then it's going to be returned on the stack. Are you going to be able to allocate 10 megabytes of data on the stack? No way. So we probably want to take a different route here. What's much smaller than a student? What's much smaller than 48 bytes? What's much smaller than 10 megabytes or something? Maybe I don't have to give this object to you. I just have to tell you that there's the object over there. What am I doing? I am pointing to it. So what if instead of returning that structure, I returned a pointer to that structure over there? Right? Lots of things are going to change, but that's a much better design. First of all, the first thing to change in the function here is that I now need a pointer, and I'm going to return that pointer instead of returning s, which I forgot to do anyway. Return s. There we go. Now, at this point in the code, on this line here, what's it pointing to? Who knows, right? Nothing in particular, right? It could be pointing to null. It could be pointing to a memory location that doesn't belong to you. If I tried to use it, I am almost positive that something would go wrong there. So what's the first thing I need to do? I need to make it point to an actual student. How do I create an actual student? Well, how do you create an actual integer? Dynamically, that is. You don't want to, let me go ahead and rephrase that. In the context of arrays, how did you create 10 integers? You called malloc. How did you create 5 integers? You called malloc. How did you create 1 integer? You could still call malloc on an array of size 1, which is exactly what we're going to do here. I only want 1 student instance. So I'm going to call malloc is equal to student star malloc. And I only want 1 of them, so you can erase that if you really want to. But I'm driving home the point that I only want 1 student here. Now, how many bytes does a student take again? Size of student. Compilers are dumb, but they're smart enough that they can go through and read code and say, oh, you need 48 bytes for that. Here you go. Right? Now I've got my pointer pointing to that 48 bytes over there that I can play with. Other things will change here. First of all, you can no longer use the dot operator, can you? I've got a pointer now. A dot operator is for a regular old structure. So what do I need to do first? I need to take this pointer and turn it into a regular old structure. How do I take a pointer and turn it into a regular old variable? Dereference it, *s. Right? And now I can use the dot operator. However, you go to your list of precedence rules and find out that, well, yes, multiplication occurs before addition, but I've actually got two operators here, the dot operator and the dereferencing operator. Which one occurs first here? Turns out that it's the dot operator. So if I'm going to do this, I need to surround that dereferencing with parentheses. Supremely ugly. That's why there's an even more convenient thing to do. Instead of using a dot operator, I'm going to use a hyphen and then a greater than sign. Except it looks like a what? It looks like an arrow, so we call it an arrow operator. Now again, it has a technical name. It's the indirect component selection operator. Just call it the arrow operator because it looks like an arrow. Right? All right, I'm going to continue to do that all over the place. I'm going to have to replace all those dots with arrows. Arrow, where else? Arrow, then last name, arrow, 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 arrow. There we go. And now I can return that, that pointer. Okay? I also need to change how I'm using them down here. Instead of a student, receiving a student back from that function, now I'm going to be receiving a pointer to it instead. Okay? And so I've got Joe and Jane, and if I ever want to access any of their elements, then I need to use the arrow operator because I've got pointers to structures here. Now you'll note here on this chunk of code right here, I was using a combination of arrows and dots. Why? S is a pointer, so I need to use the arrow operator to get to the date of birth. But once I'm at the date of birth, let's go up to the definition here. Date of birth. Is that a pointer? Nope. So I use the dot operator instead. Okay? All right. So there you go. That's basic usage. Again, the takeaways here are generally it is better to use pointers to structures as they can be potentially large. All right. When you using a pointer to a structure, you use the arrow operator, that is the hyphen and then the greater than sign, to access member variables. Right? When you have a regular old structure, you can use the dot operator. There's a dot operator. Right? Okay. And it's best practice to, it's at least convenient, if not best practice, to always make sure that you are creating factory functions, right? I could go back and redesign this and create a factory function for a date, and then I wouldn't have to pass in the day, the month, and the year all separately. I could pass in a date instead. That's not a design decision I made here. You'll find that there's always a trade-off. Right? Some people might be really dogmatic about it and say that you always need to make factory functions no matter what, and always use those factory functions. Or factory functions always have to be a certain way. It's a design issue. It becomes a debate as to the benefits and the trade-offs and the advantages and the disadvantages for what you're designing. Right? As long as it makes sense. There are some designs that are clearly bad. There are some designs that are clearly good. But everything else is in the middle, and you can debate about it. Okay. All right. Well, as another exercise here, write a function that prints a student structure's information to the standard output. Right? Once we've got students represented in our code, obviously we'll probably want to print them out, like you did yesterday in your lab. You printed out MLB teams so that you had records, and then you had columns of data. Right? You'll want to do the same thing, say, with your structures that you're defining. So let's go ahead and write this function here. All right? What should we call it, first of all? Should I call it print? Is that a good idea? Print what? And also, probably print might be a reserved word somewhere else, right? There can only be one print. So should I call it printf? Certainly I can't. What am I printing? I'm printing a student, right? Is it returning anything? What do you think? Probably not, so let's make it void, right? But it is taking a student, student s. How am I passing it to the function here? If I just have int x, I'm passing a copy of the value of x. That was called pass by value. If I had a pointer, int star x, I would be passing a pointer to x instead, in which case I would be passing a memory address. That was called passing by, not passing by value. What's the other one? Passing by reference. Right now, as it is, I am passing by value, meaning I'm taking all 48 of those bytes and I'm copying them onto the stack, and I'm really abusing that stack by copying so much memory. 48 bytes is not that much memory, but again, think about a structure that represents an MP3 file. Are you going to be able to copy 10 megs of data onto the stack? Probably not. What happens when you've got a 4 megabyte stack and you try to copy 10 megabytes onto it? What was that called again? Stack Overflow. They just celebrated their 10th anniversary a couple days ago, right? That's the major site for basically, it's the Wikipedia of coding, right? So we don't want to risk a stack overflow here. We don't want to abuse the stack. We don't want to copy 48 bytes. Instead, let's only copy 8 bytes for a pointer. Now, we did the same exact thing when we passed say an array to a function so that we could print the entire contents of the array. But what's something else that we did with that array? If you're just printing an array, are you going to change it? Probably not. So what did we do with an array to make that promise? I promise I am not going to change. I guess this is not a promise. I promise that I am going to make no changes to your array. I'm just going to print it. Right? Const. You can do the same thing here. I'm not going to make any changes to your student. I'm simply going to access its elements and print them out. Right? All right, so let's say, I don't know, let me go ahead and just say printf %s. In other words, last name, first name. So s, last name, s, first name. So last name, comma, first name. What else should we print? Let's go ahead and print their NUID in parentheses. %d, NUID, s, NUID. Right? Now here, this goes back to what we've started with our decision to use an integer or a character, or a string. If we had went with the original with a string, there would be no problem here. It would print leading zeros. As it is, somebody with only 6 digits and 2 leading zeros in their NUID, those 2 leading zeros are not going to be printed with this formatting right here. Here's a trick. 0, 8. The 8 is printing at least 8 columns. The leading 0 there is saying, don't print spaces as your leading columns, print zeros as your leading columns. So if there's an NUID out there that is 1, 2, 3, 4, 5, 6 with 2 leading zeros, it'll now automatically print those 2 leading zeros and then 1, 2, 3, 4, 5, 6. Awesome. Right? Again, the magic of printf. And then let's go ahead and print out their GPA out to, say, 2 digits. I won't worry about their date of birth. Right? And unfortunately, it's too long, so let me go ahead and break it. There we go. There. I didn't want it to go down that far. Wow. Okay. There. I just broke it across the line so that you could actually see everything. Okay? And that seems like it's it. Right? What if I wanted to print to a file? What would I have to do instead? I'd have to open up a file, use not printf, I'd have to use what? fprintf, right? And so I'd have to write another function. Print student to file. What if I wanted to print it to something else? What if I wanted to print it to a socket because I'm talking to another computer remotely and I have opened up a socket and I want to send that data to it? Well, now I need a third function, right? What if I want to print it to some other device? To print it to, not in this day and age anymore, but what if I actually wanted to print it to a printer, right? How do you send something to a printer? You open up a file and you write to that file, and then the printer takes care of it. What if you wanted to print to some other device? Function after function after function after function. What ties them all together? What is one thing that I could take and instead of cutting and pasting this line and adding fprintf, print to a file printf, print to a socket printf, all that stuff, what if instead I had a more general function? Let me go ahead and give you the name of that function. The student to string. There we go. What if I had that function instead? That took a student, say the same exact thing here, a const student star s. It takes a pointer to a student and makes the promise, I'm not going to change it. And then it prints it to a string, right? So that you can take that string and now you can do whatever you want with it. You can print it to a file, you can print it to the standard output, you can print it to the printer, you can do whatever you want with it. And now I'm not cutting and pasting the same formatting code over and over and over again. What would it look like if I did this instead? What would it look like for the return type on student to string? You give me a student, I'm going to give you a string. So, char star. Right. Now, if I'm going to give you a brand new string, just like you did in previous hacks and as you're doing hopefully right now on homework 4, you need to dynamically create a new string. I'll call it, I don't know, result, right? Is equal to a call to malloc, char star, malloc, size of char, and here it times what? Here's where we get tripped up. How many bytes are you going to need for this string? Okay, well, let me go up to the formatting here. Okay, I've got the first name, the last name, a comma and a space. I've got another comma and a space. I've got GPA, which is going to be, you know, 3 numbers with the period there, so that's 4, and I've already lost count. Right? I don't want to have to think that hard. So let's instead create a temporary string that is going to probably be big enough. I'll call it char buffer 1000. Right? What is a buffer? Go to YouTube. What does it start doing? Plays the ad first, and then now what is it? Unless you've got, I've actually never seen any ads on YouTube because of all my ad blockers. But what happens after the ad? I would suggest you do the same, right? What happens after the ad? It starts playing. What about the play button down there? What happens? It starts filling up with data, right? And then you start consuming that data by playing the video. Then when you get close to the end, hopefully, it loads more data. Where is it loading that data? What is that called? It's called a buffer. Right? You put stuff in on one end as you consume it on the other end. Another way of looking at this is a data structure called a queue, a line. Things go in one end of the line and then they come out the other end of the line. Right? People queue up in a line at a bank to go up to the teller for service. Right? And they wait in line until they get their service on the other end or whatever, right? So we have the same thing, a buffer, a temporary workspace where I can print something to it and then ask, well, how big was it without doing all that complicated arithmetic, right? I'll show you how it works here. I'm going to print the student to the buffer, right? So printf. In fact, let me go ahead and grab this up here so I don't have to repeat it. There. That would be printing to the standard output. How can I print to a string instead? Do you remember that? There's printf to the standard output. There's fprintf to print to a file. What if you wanted to print to a string? Sprintf. Right? And it's going to have a string as its first argument here. There we go. You're going to take this formatting, it's going to fill in all those placeholders, and then it's going to put the result into the buffer. How long is that? Well, now I just need to call strlen. Right? Char star result is equal to char star malloc, size of char times strlen of buffer, right? And now I don't have to do any math at all, right? Make sure I've got enough parentheses there, though. And it's cutting off, so let me go ahead and cut off there, right? By using that temporary buffer space, that 1,000 characters is probably going to be long enough. Nobody's going to have a first name that is 5,000 characters, hopefully, right? If it breaks, then we can come back and revisit that issue. But probably that's a larger sign of some bad data that we've got being processed. And then I will strcpy into result the contents of the buffer, there we go, and return result. There we go. So a brand new dynamically allocated string with a minimal effort of thinking about how many bytes we actually need for this by using a temporary buffer to store the result. Now, do we have to free that buffer? When do we have to free? When we use malloc. Did I use malloc on buffer here? Nope. It was statically declared. Here's your call stack. There's 1,000 bytes on that call stack, that stack frame. When I return back from this calling function, what happens to all that memory? It gets popped off for me, and I don't have to worry about it. Right? This is one of the few instances in which I would advocate using static strings as temporary buffers. It's still not 100% safe because, of course, you could have somebody whose last name is 1,200 characters, but that's unlikely, right? If you ever did have that situation, then you need to come back and rewrite this. But don't worry about it until you actually you'll cross that road when you get to it. All right. How does that change our first function here? Char star s is or I can't use s anymore. I'll use str instead. Is equal to a call to student to string of s. Right? And then I can use printf %s, say end the line too, right? And str. I don't know why that's being highlighted, but maybe because I was highlighting it at one point. There. Now all of the formatting information is in one place. If I'm using this in multiple places to print to a file, print to the standard output, print to another device or something like that, now I only have to worry about the formatting in one place. If I want to come back and change the formatting to first name space last name, or maybe I want to add a middle name, I only have to come back to one function and change it there. And anywhere that you're using that function, it's also changed there. Now there is an issue here. What about that string? Here's your student. You gave me a string. I print the string, and then I return. What happened to this string? It was dynamically allocated, right? str was created with malloc. So if I'm done using it, what should I do with it? I should free it. Right? So free str. There we go. Okay. With only 10 minutes left here, what I want to do, we'll save the rest of structures for later. What I want to do is I want to go to the command line here, and I want to demonstrate a tool that is going to be useful going forward. Let's see. Do I have Valgrind? No. Okay. SSH. Have I demonstrated Valgrind in here yet? Yes. Oh, I did. Oh, okay. I demonstrated GDB, the debugger, but Valgrind? I did. Oh, okay. Then so be it. I won't do that. Unless you really want to see it again. Yes? Okay. There's some disagreement here on whether or not we've done this before. I did put it into that code troubleshooting guide, if that's what you're thinking about. I put in how to, in fact, let's bring that up. Let's see, GitHub. There we go. Documents, and then troubleshooting. There we go. So this troubleshooting guide I posted maybe a week or two ago. If you get stuck, what should you do? Well, number one, test. You don't know what's wrong unless you can reproduce it locally, so that you can run it through a debugger, GDB, so that you can actually view things and what's going wrong. The second thing that you should do is the thing that I've been telling you from week 2. Always use WALL. Always turn on all the warnings, and it'll tell you about pretty much everything that is going to that the compiler can. You forgot a placeholder, or you have uninitialized memory, or something like that. WALL will tell you about that. There's also another compiler on CSE that I had them just install maybe a couple of weeks ago, which is LLVM or Clang, or some people call it CLang. I like to call it Clang, right? It sounds much better. And then you can analyze it and use it as a linter. Clang will sometimes catch things that GCC does not. So I would recommend using both of those things in parallel. You can use a dynamic analyzer like Valgrind. Valgrind, we're going to check for memory leaks here. This is actually something that I just added to Lab 7. It wasn't in there before, but I have since added it. Let's go ahead and create, I don't know, Emacs student.c. Right. And what I'm going to do is I'm going to cut and paste the functions that we had before. Well, include stdio, include stdlib. There we go. There are my functions from before. But I'm going to intentionally cause a memory leak. I'm not going to free up that string. Okay. Now let's go ahead and create a main. Int main int argc char char star argv and return 0. I'm going to go ahead and cut and paste the code that I used for for Joe and Jane here. Right, there we go. Oh, I need the factory function though too, don't I? And then I also need to cross my fingers and hope everything compiles and I didn't make another mistake. Although I think I did make a mistake. Somebody called me out on it earlier, missing semicolons. Oh, I don't even have the definitions here. Okay. Where is... There, these are definitely fixed. Right? So, oops. I grab all of it. There we go. So big giant file. Again, you don't want to do something like this in practice. I'm just doing a demonstration here. And then we'll go ahead and print student Joe and print student Jane. Right? Now I'm going to cross my fingers here and hope that everything works. std gnu99 wall, right? And student.c. Oh, that's easily fixed. What did I not include? String.h. If you're going to do string stuff, you need the string library. And kill all that. Darn it, what's wrong? Student, did I not have student to string? Student to string. No, I don't. Okay. So where is it? I just need to cut and paste it. Oh, you know what? Same problem as before here. If you're going to use it, it needs to be where? It needs to be before you use it. Generally, that's not an issue because you're using prototypes. Right? And now we're only down to 2 issues. Too many arguments for format. Okay, so there, the WAL is saving me from myself there. Student has no member date of birth because I misspelled it. I spelled it with a capital D, right? And that was on line 59. So that's wrong. And what was the other line? Anybody remember? There. 1, 2, 3, 4. Okay. Maybe it just doesn't like that white space. I have 4. Oh, okay. Thought 2%. There we go. Thank you. All right. Yay. It works. A.out. There we go. Joe Schmo, comma Joe. His NUID with those 4 leading zeros. So we did pretty well here. Except for we didn't, we have a memory leak. Right? And I wanted to demonstrate Valgrind and diagnosing that memory leak. So this is generally what I would suggest that you do. Valgrind, leak, check, everything. A full leak check for all of your memory leaks. Show leak kinds equals all, and a.out. We'll go ahead and run it. It was pretty quick. Oops. What was wrong? I need hyphen. There we go. There we go. All right, there's a report. And let's go all the way up to 4 bytes in 1 blocks are indirectly lost in a loss record of 1 of 8. So there are 8 records here that I've got memory leaks everywhere. Some of it is going to be cryptic. Of course, I called malloc at some point, but it was created in student. So what this report is telling you is that when you called malloc in create student, that returned memory never got freed up. It got returned back to whatever it was, from student to string, or actually no, this is another memory leak here in create student. Why? Oh, because the first name, last name never got cleaned up either, and so that's why it's complaining about that. I should have done that, but there's the report that I really wanted. In print student called student to string called malloc, and the memory that was allocated in that function was never freed up. Right? It was leaked. 1 blocks are definitely lost in a record of 6 of 8. So I've got a whole bunch of leaky memory all over the place here. I have 8 of them here. Let me go ahead and fix that one that I know about. There we go. GCC, and run it again. And at least 2 of those instances will probably be gone, right? Yep, 6 of 6. So I got rid of 2 of those instances of creating that string and then never cleaning it up. If you want to know how you can clean up absolutely everything before the end of the program here, well, I would have to clean up Joe's first name. I would have to free Joe's last name. And then once I have those free, what else do I need to free other than Jane? I need to free Joe. It was dynamically allocated as well. There's 1, 2, 3. Jane is the other 3. And if I cut and paste all of this and change it to Jane's first name, Jane's last name, and then finally clean up Jane herself, run it. No memory leaks at all. Wonderful. Now there's no guarantee that there aren't memory leaks. It's just that Valgrind couldn't find any. Right? By the way, sometimes cleaning up a structure, creating a structure is called constructing, right? And so you have constructors. Cleaning up up an entire structure is sometimes referred to as a destructure, because you're destructuring it. So if you really wanted to, you could write like a free student in which you did all 3 of these things, and you wouldn't have to worry about that. You'd have just a function to do it for yourself. Okay? All right, any questions? All right, I'll see you next week.